LPN. LP means low pass filter, and N means it represents time domain sequence, time domain representation, and then we convert it into frequency domain with uh, uh, transfer function H, capital H, LP omega, this one. So that characterize low pass filter frequency response. It is maybe in H, generally it is H of Z, but in place of Z, actually it is e to the power j omega. So we don't write e to the power j omega, we simply write H of omega. Now, having this any defined characteristics of low pass filter, we can convert it into high pass filter by changing the variable omega, frequency variable omega, by omega minus pi. Okay? Because suppose in low pass filter, uh, gain is high at low frequency and gain is low or zero at high frequency. Okay? But in high pass filter, it is opposite. Gain is high at high frequency and low at low frequency. High frequency means frequency pi. Low frequency means frequency 0, that is omega. So in the term omega minus pi, okay, if you write omega is equal to pi, then it should be pi minus pi, that is 0. So HP, that is transfer function of high pass filter, HP omega is equal to pi, that is at pi, that is equal to HLP omega minus pi, and if omega is pi, so it is 0. So high pass filter gain would be equal to the low pass filter gain at omega is equal to pi, that is HLP will be 0, HLP 0, that means gain is high. So this way we can convert the high pass low pass filter to high pass filter. Similarly, if the frequency omega is 0, okay, that means low frequency gain for high pass filter, it would be HLP 0 minus pi, that is minus pi. That is the mirror image of the gain of low frequency at minus frequency or minus pi. So that is 0. Okay, so we'll get 0 frequency, okay, at 0. 0 frequency, we get 0 gain, okay, at 0 frequency for high pass filter. Now this is the translation formula of low pass filter to high pass filter. Just changing the variable omega by omega minus pi. Okay. Now, if this is the formula that we are translating the frequency variable, so according to the property of Fourier transform, okay, what happens, or Z transform, what happens if the frequency variable is shifted by some value? So what effect is there in time domain? In time domain, it will be multiplied by e to the power j pi n. Okay, e to the power j pi n in time domain. So high pass filter impulse response HHPN is equal to the impulse response of time domain low pass time domain of low frequency HLP multiplied with e to the power j pi n, that we using frequency shifting property. So e to the power j pi, you know, it is -1. So it is -1 to the power n h of LPN. So this is the formula or effect in time domain. Okay, when we translate the frequency variable or we convert the low pass filter to high pass filter. Now consider the difference equation that describes any filter, that is yn is equal to k is equal to 1 to n ak yn minus k, where k is 1, and for so that means past values of output, okay, and past and present values of input. This minus side actually comes from the general formula. So for this case, what is the frequency? What is the frequency response? We calculate it as, if you take the if you use this property that HLP omega, that is output by input, okay, y omega by x omega. So y omega is what? It is the Fourier representation, or you can say Z domain, by replacing the variable Z to e to the power Z is equal to e to the power j omega, and from the Z transform, okay, of what is the formula for Z transform, that xz into z to the power minus n. So it is one way. Another way is you just we are delaying it. There is delay in the output signal. So each time the output signal is delayed, it is multiplied with z inverse, okay, or e to the power minus j omega. So we add all those terms, so we get this expression, okay, that you can recall from our earlier discussion, that now it is coming to be this one, this by this. Okay. So in this equation, this is the equation for low pass filter. In this equation, if you replace omega by omega minus pi, so simply we multiply according to this relation, -1 to the power un hl lpn. So we get multiply by -1 to the power k, each term. Okay, so we get this expression, it becomes high pass filter, and which corresponds to the difference equation this. Okay, just we are inverting inverse Z transform or inverse Fourier transform, we get the difference equation this one. Now we describe this with low pass filter. Another example. Okay, so convert the low pass filter described by the difference equation into a high pass filter. So your formula is yn is equal to, input output relation is yn is equal to 0.9 y of n minus 1 plus 0.1 xn into, this is the expression for low pass filter, input output relation. What will be the relation in this high pass filter? So the difference equation for the high pass filter, according to this equation 5.4.18, that is this. Okay, you just multiply with -1 to the power k. Okay, here k is only 1 because y goes up to n minus 1, yn minus 1. So k is 1. So we get -1 to the power, for k is equal to 1, we get minus for this one, and 0.9 is the value of this ak coefficient a1 into y of n minus 1 plus 0.1 here k is equal to 0. Okay, so no shifting, and k is equal to 0 means minus 1 to the power 0, that is 1 only. So it is not minus 1 now, so we get x of n according to this. So this is the difference equation for high pass filter after converting. So its frequency response would be what? Okay, it is just convert it into z domain. Yz is equal to minus 0.9 into z inverse yz plus 0.1 into xz. Now taking common yz, so yz into 1 plus 0.9 z inverse is equal to 0.1 xz. Now yz by xz, okay, yz by xz is equal to 8z, that is equal to 0.1 by 1 plus 0.9 z inverse. Now in frequency domain, okay, just in place of z is equal to z, we write e to the power j omega, so it becomes e to the power minus j. So this is actually high pass filter. Okay, so where pole is at minus 0.9, okay, you can say that z is equal to minus 9, minus 0.9. So poles lies left hand side of the z plane. Okay, so or near to unit circle, so that means z is equal to minus 0.9, so that means it is indeed high pass filter. Okay. As we have seen in earlier cases, that what should be the locations of poles and zeros. So the locations of poles and zero we have understood. Is it clear?
Yes, sir.
10 minute later. So now these are the topics up to this we can consider as the as from the module 1. Okay, further some advanced topics are there, like digital resonators. Okay, digital resonator is what we can see that resonator means at some particular frequency gain is very high. Okay, so we can see that at this in the graph at this frequency gain is very high. Okay, so it is resonating at some point. So the process is what, that let us say we want to design a resonator or uh, resonator at having gain, maximum gain at omega is equal to omega 0. Okay, so we should select the poles as R into e to the power plus minus j omega 0. Okay. So this is the locations of poles. Uh, so although there are many possible choices, two cases are of special interest. One choice is to locate the zeros at the origin. Okay. Zeros at the origin means omega is equal to 0. वहाँ पे हम लोग एक जीरो कर सकते, so that फ्रीक्वेंसी ओमेगा 0 पे गेन 0 होगा. और other choice is to locate a 0 at z is equal to 1. Okay. z is equal to 1 मतलब वही सेम चीज है, ओमेगा इज इक्वल टू 0. okay. तो दो एक जीरो हो जाएगा ओरिजिन में, और एक जीरो हो जाएगा z इज इक्वल टू 1 पे, और एक जीरो हो सकता है -1 पे, मतलब हाई फ्रीक्वेंसी में जहाँ पे गेन 0 होगा. तो ये 3 जीरो होना ही चाहिए, z इज इक्वल टू -1. Okay. So this with this, we write the transfer function of resonator, okay, considering the two poles, complex conjugate poles located at r into e to the power plus minus j omega 0. So it is one is r into e to the power j omega 0 and another is at r is equal to e to the power minus j omega 0. So if you multiply this, then you will get this kind of expression. So we get two poles at these two locations. Okay, this here one and here it is plus. It is plus omega 0 and it is minus omega 0. Now, if you go through the all discussion, okay, so you can find the values of B0, okay, the gain, okay, according to the criteria. Okay, R is equal to 0.8. So it is the value of R. What value we should choose? The radius, okay, of jet plane, magnitude of that pole. So R is equal to 0.8. These characteristics. R is equal to 0.95. Sharper characteristics, more sharper. So this I am not discussing. Then just I am touching all these things. Notch filter. Okay. So there we have assumed, in the case of resonator, we have assumed poles should be there at a corresponding frequency, and we have set the poles. But in case of notch filter, okay, notch filter characteristics is this one, that at some frequency, in the positive frequency, there is notch, means gain is zero. Gain is zero here. At this point, gain is zero. So we should locate zeros at that frequency. That is e to the power plus minus j omega 0. Okay. So in place of omega, we write omega 0, and we should choose complex conjugate zeros, because gain will be zero at those frequencies. So we choose the zeros there, and in the transfer function, we keep those two zeros, okay, like 1 minus e to the power j omega 0 z inverse and 1 minus e to the power minus j omega 0 z inverse. So what happens? This actually only numerator. Okay, only numerator term is there. And in this case, here only denominator term is there in the resonator. And in the notch filter, only numerator term is there. So again, discussions are there. So how to modify this type of characteristics with some other, you can add some poles also, okay, to further modify the filter. Okay, then comb filter. Comb filter is what? Comb filter is this kind of response. A different at different frequencies, we will get multiple peaks. There are different frequencies at which gain is high. Okay, so this looks like a comb. The gain is high at those frequencies. So what is the filter design and all, it is given there. Okay. So since I am not getting time, you can see it. If you have any, if you find any interest, then you can design this also using MATLAB or any other technique. Okay. So and just go through it, whosoever find interest. Okay. Then all pass filter, what should be the pole zero locations that is given. Okay, so now it is finished. So anybody wants to have any discussion regarding this? Any doubt? Today's first module is over. Okay. Do you want any times of discussion?
No, sir. No, sir.
Any information from the other section?
No, sir.
Okay. Okay, today I will talk with him, Vishal Shah sir, and will let you know.
Sir, what will be the format of quiz?
It is objective type, not many questions, okay, but I think 15 to 20 minutes.
Yes, sir.
15 to 20 minutes.
Yes, sir.